Here I have a function, f of x is equal to x minus 3 times x plus 1 squared. On the right, I have the graph of the function. I used some graphing software to graph this. I want to talk about some things about this graph, what we notice about the graph, and how it relates to this equation here. One thing to notice that this is a polynomial function. The graph is really smooth and continuous. You notice that at any turning point here, we have a nice rounded shape, and we can draw this graph without lifting our pencil. If we wanted to, we could FOIL this out and put it in that form, a sub n x to the power n plus a sub n minus 1 x to the n minus 1 and so on. In fact, I'm going to do that pretty quickly here. I'm going to FOIL this. This is x minus 3 times x plus 1, x plus 1. I'm going to multiply these two in the back first. And I get x squared plus 2x plus 1. And then to multiply this, I distribute the x to everything. I get x cubed plus 2x squared plus x. And then distribute the negative 3. And just combine like terms. Now I did that pretty fast, but I think this is what you'll get if you expand this. So I'm going to erase all of this. So if we wanted to put this function in a nice polynomial form, let me write it here. This is the same thing as x cubed minus x squared minus 5x minus 3. So notice that the leading term is x cubed. It turns out that the end shape of this function is going to look very similar to the power function y is equal to x cubed. So here I have something whose leading term is x cubed. So the power function y is equal to x cubed, remember, that looks like this. We have an odd power, and the number in the front is 1, which is bigger than 0. So it just looks like this x cubed function. Notice that on the ends, right here and down here, this kind of looks like x cubed, except for in the middle. In the middle, we have something more complicated happening. So one thing to note is that whenever you have a function like this, the leading term tells you what the end shape of the function looks like. So we have x cubed, so it kind of looks like an x cubed. So make sure you write that down. We're going to use that a lot. Oops. That's very strange. Let's see if I can fix this. Okay. All right. Now to find the leading term right here, you don't actually have to FOIL all of this out. To help you graph this function, you only need this piece. All of this other stuff, at least for right now, you don't have to know that to figure out the power function. To figure out the leading term, you just look at the function here, and you see that this is raised to the first power, so I have an x to the first. And if I FOILed this out, I'd have an x squared. And so if I multiplied everything out, the leading term, the highest power would be x to the 2 times x to the 1. So you would have x cubed. And so that would be the term, the leading term would have the power 3. That's the highest power in this polynomial function. So your graph is going to look like x cubed. The next thing I want to notice is that we have two roots. We have the roots x is equal to 3 with a multiplicity of 1, meaning that the root 3, notice it's a root because if you plug in 3 here, you get 0. And remember, to find a root, you set the function equal to 0 and solve for x. Here, the power on this factor is 1, and that's what the multiplicity is. And we also have the root -1, and its multiplicity is 2. Okay, let's look at the graph. You can see that I have a root at -1, 0, and a root here, x is 3, so at this point, 3, 0. Remember what we learned in the last video. If the multiplicity is odd, then we go through the x-axis at that point. If the multiplicity is even, we just touch the x-axis, and that's what you see here. Right at 3, we go through the x-axis, and at -1, we just touch the x-axis. Okay. Something else we can notice is that we have something called turning points. Turning points are where your function goes from increasing to decreasing or from decreasing to increasing. So increasing to decreasing. And that is where you have a maximum, or your function goes from increasing, goes from decreasing to increasing. And that's where you have a minimum on the graph, a relative minimum. So let's look at this function here. I'm going to erase these 2 points here. And let's see how many turning points we have. So this function, notice that its range is from -infinity to +infinity, and so is its domain. From -infinity all the way to this point, which is x is -1, we are increasing because the graph is going up. And then from -1 to this point here, we're decreasing. You can see that the function's going down. And then at this point, whatever that is, and onward, we're going up. So we have 2 turning points. We have a turning point here and a turning point here. It turns out that if you have, let's say x is equal to the number of turning points, then the maximum number of turning points, let's say n is equal to your degree of your function, then the maximum number of turning points is equal to n minus 1. So for our particular example, remember that this function, its degree is 3. Remember when we FOILed it out, we got an x cubed term. This was equal to x cubed plus some other stuff. But the degree was 3. That was the power on the leading term. And we had 2 turning points. Now it is possible for you to have less than 2 turning points for a degree 3 function. So what I'm saying here is, where n is your degree, the maximum number, so the most turning points you can have, is 1 less than the degree of your function. You can have less than that, but the most you can have is 1 less than the degree. So if you have a degree 3 function, then you can have no turning points, you can have 1 turning point, or you can have 2 turning points. In this example, we had 2 turning points. Okay. Let's move on to another example. Here I have the function x plus 1 squared times x minus 1 squared. Okay, let's go ahead and start writing some things down. At first, I want to figure out the degree of this function. How can I do that? Well, I can FOIL this out and write it, expand it, and write it as a full polynomial, but all I really need to know is the leading term. That will give me the degree. So notice if you FOILed this, x plus 1 times x plus 1, you're going to get an x squared plus some other stuff. And the other stuff will have lower powers, because you'll get like a 2x and a plus 1. And then over here, if you FOIL this out, you're going to get an x squared minus 2x plus 1. But I really don't care about this other stuff, because when I multiply these two trinomials together, I'm going to get x to the 4th plus some other stuff. So let me write this. So what this will end up being is x to the 4th plus some other stuff with lower degree. This is going to be your leading term. So your degree is equal to 4. And notice that this is even. And notice that your leading term is 1x to the 4th. And that's the power function that this function is going to resemble. Now I went ahead and graphed this, like I said, with some software here. And 1x to the 4th, remember that x to the 4th looks like a parabola. And here you have something that looks like a parabola, at least on the ends. And in the middle, something strange happened. But the overall shape here, on the left and the right, is like a parabola. And it's pointing upward. And that's because the coefficient here, the leading coefficient, is 1, which is greater than 0. Something else we can notice is that the zeros for this function are 1 and negative 1. So let's write that. The zeros, or the roots of this function, are x is equal to negative 1 and x is equal to 1, and they have the same multiplicity. They both have multiplicity 2. And what happens at these 2 points? You can see that this is negative 1, and this is positive 1, and that this function touches and goes, touches and goes. It doesn't intersect. It doesn't go all the way through across this x-axis. Okay, and let's count the number of turning points we have here. So that means find the number of maxima and minima you have. So here I have a minimum, here I have a maximum, and here I have a minimum. 1, 2, 3, so I have 3 turning points. And notice that I have a degree 4 polynomial, and 4 minus 1 is 3. I have the maximum number of turning points allowed for such a function. And we could actually find these points. Here, these are the x-intercepts, and this one is the y-intercept. So you would just plug in 0 for x to find this point. Okay, let's move on. This function is a very strange looking function. I have y is equal to negative 1 over 10,000. I had to put a big number on the bottom of this fraction in order for us to be able to see this when I graphed it. And notice that I have the roots 5, 1, and negative 4, and their multiplicities. So let's write down some information. First, the roots. The roots are 5, 1, and negative 4, and underneath them I'm going to write the multiplicity. I'm going to put m for multiplicity. The multiplicity is 4, the multiplicity here is 2, and the multiplicity here is 3. Because the multiplicity here and here is even, we're going to touch the x-axis. And here we're going to cross, because this number is odd. Let's see if that's true with the graph. Here, this is the only negative intercept, so this has to be negative 4. And you can see we cross the x-axis. And then we had the roots 1 and 5. So this one has to be 1, and this one's halfway between 0 and 10. And you can see we just touched the x-axis there. So this is true. The next thing is, let's count the number of turning points. Okay. So I have a turning point. Remember, a turning point is where you go from increasing to decreasing or decreasing to increasing. So I have one here at this bottom section, one here, and one here. So 1, 2, 3, 4. I have 4 turning points. I'm going to write that here. 1, 2, 3, 4. Now this point is actually a very interesting point. It's not a turning point because you're going from decreasing to decreasing. It's actually called a point of inflection. You'll learn a lot more about that in calculus. But right now, maxima and minima are turning points. Now let's find the degree of this function. And let's also determine the power function that it resembles. So up here, I'm going to put the 4 turning points because I want to remember that. So let's find the leading term. And that means if we FOILed all of this out, what would be the leading coefficient and the whole leading term, that is the x with the highest power, and that tells us the degree of the function. So if we FOILed this, expanded this, we'd have x to the 4th plus some stuff. If we FOILed this, we'd have an x squared plus stuff. And if we FOILed this, we'd have an x cubed plus stuff. Now, if we multiplied all this out, we'd get an x to the 4th times an x squared times x cubed. 4, 5, 6, 7, 8, 9. We'd have x to the 9th. So that would be the degree, n is equal to 9. But what is the leading coefficient? So here, notice that the numbers in front of these x's are all 1s. And if we FOILed them out, we would just get this x to the 9th. But on the outside here, I have a negative 1 over 10,000. So we need to put that in the front because that negative 1 over 10,000 would be distributed to everything inside. So that is going to be the leading term. Okay, the degree is odd, which tells me my graph is either going to look something like this or something like this. It's going to resemble the power function x to the 9th. But because the coefficient in the front is negative 1 over 10,000, that number is less than 0. It's a negative number, which tells me that the whole function is going to kind of resemble this flipped version of x cubed. Remember, anything with an odd power looks like the graph x cubed. And you can see that. Here, this is going up like x cubed. And then something strange is happening in the middle. And then on the end, this is going down like x cubed. Exactly what we expected. Now notice that n is 9 here, and we only had 4 turning points. The maximum number of turning points would be 8. It is possible to come up with a function like this. Maybe if we got rid of this 10,000 or some of the multiplicities were rearranged or something, we could get something with 8 turning points. But this particular function has 4 turning points. So the max number of turning points allowed, but we only got 4 for this problem. Now I'm going to do something very interesting. I'm going to change a few things. I'm going to give you the same function. Erase this. But I'm actually going to change the multiplicities. And what I'm going to do is I'm going to reduce some of these multiplicities. I'm going to keep them, if it's an even number, I'm going to keep it even. And if it's an odd number, I'm going to keep it odd. And also I might change this fraction in the front a little bit, and that way you can see the problem better. So here's the first one. Now let's see what I've done to the second one. Let me move this up a little bit. Okay, let's compare this to the first one. here. Okay, what's different? Here I have subtracted 2 from this multiplicity. So I've given you a function where I just reduced this one, but I've left the multiplicities the same here. And I've also rescaled it a little bit. I kind of stretched the graph a little bit, because if I don't do that, then you wouldn't be able to see it with graphing software. But it doesn't really matter about this number other than it being positive or negative. Okay, let's compare this graph to the graph I had before. Notice that they're very similar. In fact, maybe we can put them side by side. So what I'm going to do is I'm going to move this one over here. So this was my original graph, and this is the new graph. And notice that they both go down and intersect, they cross here, and they touch and touch here. And also notice that here I've kind of made this, see, this is from 0 to -10, but now I have a wider section that's 0 to -10. They look almost identical in a way, like the whole overall picture is very similar. Although yes, I do go down a lot further here, but they are similar. So if we were sketching a graph, you know, this graph could pass as this graph if we weren't very careful. But notice the similarities. Like I said, we touched here, and that's because of these multiplicities. Again, we have even, even, so we touch, touch, and here we have odd, so we just cross here. We have a negative in the front, and the degree for this particular polynomial is x squared times x cubed, which is x to the 7th. So the power function here is -1 over 1,000 x to the 7th. This is an odd number, so it's going to look like x cubed, but it's going to look like this because of the negative, just like the other function. And we have 1, 2, 3, 4 turning points, the same number of turning points as the other graph. But remember, for this particular function, you could have 6 turning points. That would be the maximum number because of the degree. Okay. And now I'm going to do one more thing. I'm going to reduce this x plus 4, this multiplicity, to 1. And then I change the number in the front. And look what happened. We get a graph that's very similar to the other ones. So by changing the multiplicity, although I'm decreasing them, I'm keeping the even multiplicities even and the odd ones odd. Here I have x squared, x to the 1st. So my degree for this function is x to the 5th. And just like the other ones, I have 1, 2, 3, 4 turning points. And here you can see the degree is 5, so it's 1 less. So the 4 would have been the maximum number of turning points allowed. You can see that the power function is -1 over 100, which here you can see that this kind of looks like -x cubed, just like the other ones. Yeah, they look very similar. And that's what happens. As long as you keep the even multiplicities even and the odds odd, you can kind of move those numbers around. And as long as you keep this negative, if changing this number in the front will kind of stretch or compress your graph. Okay, let's move on. Here I'm giving you a problem that's actually in the book. It says, which of these graphs in figure 13 could be the graph of a polynomial function? And for those that could be a graph of a polynomial function, list the real zeros and state the least degree the polynomial can have. For those that could not, say why not. Okay, so for those that are not a polynomial function, let's say why they're not polynomial functions. Let's start with this first one here. A. What's wrong with this function? Notice that, remember, polynomial function is smooth and continuous. That means I can draw it without lifting my pencil. That's the definition of continuous. Here I have a break. To go from here to here, I have to lift my pencil. So this is not a polynomial function. Okay. How about this one? This graph is continuous. I can draw it without lifting my pencil, and it is smooth. Notice that anytime I have a turning point, I make a nice rounded edge. So this is a polynomial function. Notice that we have two turning points. Okay, so since we have two turning points, the max degree, well, sorry, let me rephrase that. The minimum degree is going to be 3. Why is that? Because remember, I said the number of turning points is always at least one less than the degree. So if the degree is 3, if we subtract 1, we would have 2, which would be the maximum number of turning points. Of course, you could have a degree 4, like in the example we saw a little while ago. If I scroll back up, here, this problem, we had a degree 5, but we had 4 turning points, which is exactly like the one below when we said 1 less. But then we had something like this, which was degree 7, and we had 4 turning points. So we can have, if we have 4 turning points, we can have a degree 5, a degree 6, a degree 7, but it always has to be at least one bigger than the number of turning points. And that's what's happening here. So since we have 2 turning points, we have to have at least a degree 3 polynomial. The zeros are -2. So let's write this here. In fact, maybe we can say -2. This is 1, and this is 2. So here, we're going to intersect or cross the x-axis. We cross the x-axis and we cross the x-axis. I can go ahead and tell you what this polynomial is going to look like. This is f of x is equal to some number in the front times x minus 2, let me erase this here, times x minus 1 times x plus 2. Now from here, let me show you what I did. I have the x minus 2 here, the x minus 1 here, and the x plus 2 goes with this root here. And because they're all crossing, you can choose whatever multiplicity you want here. They could all be 1. They could all be 3. This one could be 1, this could be 3, and this could be maybe 5. These are possibilities for the function that we're graphing. The only thing that we can't do is make one of them even. Also, we can tell a little bit about the letter A. The letter A, notice that this kind of looks like x cubed, but x cubed has been flipped upside down. A has to be less than 0. So this has to be odd, this has to be odd, and this has to be odd. And notice that the number of intercepts is 3, and we had 2 turning points. And if we have at least 3 intercepts, that would tell us that we have at least a degree of 3. So write that down, and maybe try to sketch this. I need to erase it so I can put some information for part C. Okay, is C a polynomial function? Well, the answer is no, not a polynomial function. And the reason for that is, you can see it has a sharp turn. Right here, we turn really sharp, so it's not smooth, so it can't be a polynomial function. For this one, this looks like a polynomial function. It's smooth and continuous. So it could be, it is a polynomial function. Notice that there is 1, 2, 3 turning points. You see we go from increasing to decreasing. There we go from decreasing to increasing, and here we go from increasing to decreasing. So the minimum degree is equal to 4, because we just add 1 to the to this number here, the number of turning points. We have the real roots of x is equal to -4 and x is equal to, this looks like 1. And you can see we're crossing, so this is going to have a multiplicity that's odd, and this is going to have a multiplicity that's odd. So the thing is, these could be repeated roots. So what we could do, if we wanted something that had, it has to have a minimum degree of 4, and it also has to have a degree that is even. And the reason for that is if you look here at these pieces, these are going down both sides, and it kind of looks like a parabola. So not only do we say that the minimum degree is 4, we also say that the degree has to be even. So we could do 6, 8, all of these could be possible degrees for our function. So what could happen when we want to write the polynomial function is we could say something like, an example of this, something that could potentially go with this graph would be maybe -3, x plus 4 squared, x minus 1 squared. Here, notice I put the roots just like that. Here's -4, I put the opposite in here and the opposite in here. Oh, and we want the numbers to be odd. So that tells me, because we're crossing, right? So this has to be like a 3, and this could also be a 3. Or you could put a 5 there. As long as when you add them, you get an even number, which is going to be the degree of your function, and that degree has to be 4 or higher. It can't be something like this, x plus 4 times x minus 1, because then the degree would be 2. So you need at least one of these to be a cubed like that. And maybe that one's a 1. So I'm just coming up with possibilities that could go with this polynomial function. Okay. All right. Here's another example from your book. It says, which of the graphs in figure 16 could be the graph of this function? F of x is x to the 4th plus ax cubed plus bx squared minus 5x minus 6, where a and b are greater than 0. And this figure, you can see there's 4 graphs, and we're trying to match f with one of these graphs. Let's see what we can do with this. Okay, start off. This function, its degree is 4. And the leading coefficient is 1. Remember, the leading coefficient is the number in front of the x to the 4. That's 1. And 1 is greater than 0, which tells me we have a positive number. Remember that if the degree is an even number and the leading coefficient is greater than 0, we have something that kind of looks like a parabola, and it's pointing upwards. A, B, and C are all pointing upwards, but D is pointing downwards. There's no way that this could be the graph of our function because it's pointing downwards. We would need a negative in the front for that to happen. Okay, what else can we tell? Well, we can count the number of turning points. Okay, this has a degree 4, which means the max number of turning points is 3, 1 less than the degree. Well, let's see, this one has 1, 2, 3, 4, 5. There's no way that this function here, this graph, goes with this function. So we're going to cross this one out. This one has 1, 2, 3 turning points, which makes sense for this function. And this one also has 3. So remember, you can have 3, 2, 1, but you can't have anything more than 3. So we've already eliminated 2 of the graphs. Let's see what else we can do. I noticed by looking at these 2 functions that we have a y-intercept. Okay, what is the y-intercept? Here, for this graph, the y-intercept is bigger than 0. some kind of positive number. And here the y-intercept is below 0 because this is the x-axis. Remember what the y-intercept is. It's when we plug in x is equal to 0 into our function. So if I plug in 0 into this function, so what is f of 0? I get 0 plus, I don't even care what a is, because a times 0 is going to be 0, 0, and this is going to be minus 5 times 0, minus 6. And so I end up with negative 6. Because that's a negative number, this is the only graph that could possibly be the graph of this function. Because we got a negative for the y-intercept, which would make sense for this graph. And we have 3 turning points and we're pointing upward. So we use process of elimination to figure out the graph that could possibly be the graph of this function. And here we didn't even need to know what a and b were to figure this out. All right, here I have a graph of a polynomial function, and I want to write a polynomial function whose graph is shown. So we're just trying to come up with a potential function that would fit this graph. Let's see if we can do that. All right, some things to notice is that we're pointing upwards on the ends. So this degree of the function we're going to come up with has to be even, and the leading coefficient has to be positive. It's got to be bigger than 0 in order to get something that looks like that. Okay, we have some roots. Let's talk about the roots. We have x is equal to negative 2. And the multiplicity for this one has to be even because we touch the graph here. We have the root 0 right here. And the multiplicity there has to be odd because we cross there. Here we have a root, x is equal to 2, and the multiplicity has to be odd because we cross. Okay? Whenever we have a root, that means we're going to have a factor. We're going to have a factor of x minus this root, so x plus 2, raised to that multiplicity. Here we're going to have x minus 0 raised to this multiplicity, whatever this one happens to be. And this one's going to be x minus 2 raised to a multiplicity. We just have to figure out some multiplicities. Let's also count the number of turning points. We have 1, 2, 3 turning points, which means the min number, the minimum degree is 4. So 2, 3, 4. If we let m for this one be 2, for example, and then we choose 1 for both of these. So we have x plus 2 squared. That would give us the root x is negative 2 with an even multiplicity, and then x minus 0 to the 1, x minus 2 to the first power. Well, how we can write this polynomial, I'm going to write it over here. We can say f of x is equal to a, x plus 2 squared, times x minus 0 times x minus 2. And we just choose an a that's positive because that's going to be the leading coefficient. We want something positive. In fact, you can just put a 1 here, but you can put a 2 if you like. And then let's just clean this up a little bit. X minus 0 is just x, so 2x, x plus 2 squared, x minus 2. That is a possible polynomial function for this graph. And I'm going to write it over here so we can see it with the graph. So let's put it right here, make it a little bit smaller. And in fact, you can choose any number you want that's odd to put on this x. So you could put a 3 here, and you could put a 5 maybe here, and you could put a 4 here, as long as when you add up the multiplicities, you get a number that is bigger or equal to 4, and yeah, the multiplicity for this one and this one is odd and this one's even. And this number has to be positive, okay?